All right, if 6.2 is multiplied by 10 cubed, then the decimal point moves 3 places to the right. True or false? True. Yes. True. So 10 cubed is 1,000. Quick way to do that in your head, you go, oh, 1,000 is a 1 with 3 zeros after it, and that's the number of places you move a decimal point. All right, 21 root 2 plus 10 root 2. Does that equal 31 root 4? No, what does it equal? Okay, so you did it in your calculator? Yeah. So you did this part in your calculator and you got 43.8. That's good enough. Yeah, that's good enough. The squiggly equal sign means approximately. So let's put approximately 43.8. And then you type in 31 root 4, right? And you'd get 62. Right? So, and you say, oh, those are not the same, right? So this is false. But 21 root 2 plus 10 root 2, if you were going to do that exactly, as opposed to typing into your calculator and getting an approximation, that would come out to 31 root 2. You can treat radicals like the same way you'd treat an x, right? Where like 21x plus 10x is 31x. 21 root 2 plus 10 root 2 is 31 root 2. All right, 4x squared minus 1 all squared, is that equal to 16x squared plus 1? It's a very common mistake, which is why I put it on the very first day. This is not true, because 4x squared minus 1 squared means 4x squared minus 1 times 4x squared minus 1. And then you have to distribute there. You might have learned that this is called FOIL. You might have learned lobster claw. You might have learned distribute. There's lots of different, you might have learned a box method to do this. But either way, you have to multiply everything in each set of parentheses by everything else. So 4x squared times 4x squared is 16x squared, right? So that's the first piece of your lobster claw. Then you have to do the 4x squared times the negative 1, and you get negative 4x squared. Okay. And then you do the bottom part of the lobster claw. Negative 1 times 4x squared is negative 4x squared. And then finally, the last part of the lobster claw, negative 1 times negative 1 is plus 1. Oh, yes, sorry. That should be 16x to the 4th. Thank you. Yeah, and then you'd combine like terms and you'd have 16x to the 4th minus 8x squared plus 1. So this one was false. Erase here a little bit so we can see what this next thing is. Oh, I've got two fractions. Are they actually equal? So we got to maybe reduce the one on the left, see if it equals the one on the right. So if I just look at the constants, 24 over negative 2, that is negative 12. Yeah, negative 12. And then I have, for y's, I have y to the 13 over y to the negative 2. So what do you do with a negative exponent? Yes, 1 over, or you just, a negative exponent typically indicates movement. So one way that some people remember this is that a negative exponent is like a crying baby. Sometimes a baby's crying because it wants to be picked up. Sometimes a baby's crying because it's tired and it wants to be put down, right? So this baby is already down, right? And it's crying, so it needs to be picked up. Move it to the numerator. And then the negative goes away. It's not crying anymore. It's happy. So we would move that to the numerator. So I already have x squared and y to the 13th. Those are the things that were already there. And then I have to bring up a y squared. And then I've got an x to the 5th in the denominator. Okay, so there's no more crying babies. The 24 over the -2. Yep. All right, then I have y to the 13th and a y squared multiplying like bases. I would add those exponents. So I have -12. I'll leave the x for now. I've got a y to the 15th. Y to the 15th over, and then x squared over x to the 5th. What about when you divide like bases? What do you do to the exponents? Subtract. So if I did 2 minus 5, I'd get -3, right? But then the baby would be crying, so I'd put it down. So I put +3 in the denominator. X to the +3. So that actually is the answer here. So that one is true. All right. Ooh, 2/7 to the 0. This one is kind of ugly, huh? What is 2/7 to the 0 power? 1. And then why? Somebody asked why? Oh, good question. Okay, so let me, let's just pick a easier base than 2/7. Let's say like 3. So if I have 3 to the 4th, 3 cubed, 3 squared, 3 to the 1st. What's 3 to the 4th? 3 times 3 times 3 times 3 is 81. Okay, what's 3 cubed? 27. 3 times 3 times 3, 27. 3 squared, 9. 3 to the 1st, 3. Good. All right, so let's see if we can establish a pattern here. What do you do to 81 to make a 27? Divide it by 3. Yeah, if I divide it by 3, 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. If I were to continue this pattern, on the left, I'd have 3 to the 0, right? Because my exponents went 4, 3, 2, 1. My next one would be 0. And on the right, I would divide by 3. What's 3 divided by 3? 1. 3 divided by 3 is 1. Yep. Let's continue it one more. 3 to the -1, right? Reduce the exponent one more. What's 1 divided by 3? 1/3. 1 over 3 to the 1st. We took that crying baby, put it down. It's kind of cool, right? So up until here, right, exponents meant repeated multiplication. After that, that definition no longer applies, right? We just extended, we said, well, in order for 3 to 0 to fit the pattern that works up here, it would have to be 1, right? In order for 3 to the -1 to fit the pattern that's been established, it has to be 1/3. So that repeated multiplication definition doesn't make any sense anymore. We extended the definition to mean something more. Okay, so 2/7 to the 0 is 1. Anything to the 0 is always 1. Okay, and then I've got a negative exponent here, which is a crying baby, right? So that baby is already in the numerator, right? Think of this as 32 to the -2/5 over 1, because you can put anything over 1, still the same value. So if I want to make that baby happy, I have to put it down, right? I'm going to move it down to the denominator, and then the exponent will become positive. It'll stop crying. So this is going to become 1 over 32 to the 2/5. Now the exponent's positive. Now, when you have a fractional exponent, the numerator is the power, and the denominator is the root, right? And some people remember that by remembering that roots go in the cellar, right? Roots belong in the cellar, so the bottom number is the root. So I want to take the 5th root of 32. What number can you multiply itself by itself 5 times and get 32? 2. Yeah. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2. And then I have to square it. So this is going to be 1 minus 2 squared, which is 1/4. 1 minus 1/4 is 3/4. So this one is actually false, because they put 1/4. What do you think of the next one? True or false? Got one false and one true. Anybody else want to weigh in? True? Okay, true. Yeah, the thing you're being checked here, see if you remember, is the order of operations, in that you have to do multiplication before addition. So that x squared times x squared becomes an x to the 4th, right? And then x squared plus x squared is 2x squared. And those are no longer like terms. That's as far as you can go. All right, root 50 times root 6. Is that the same thing as 10 times root 3? Deanna, did you do your calculator trick here?
Well, I only calculated, individual and time.
Oh, okay. So you're not sure if the answer is yes or no yet? Okay. So that's one way you could do it, right? You could just type both of these into your calculator and see if they're the same. When you're multiplying two radicals, like root 50 times root 6, you can actually multiply the 50 and the 6, right? So root 50 times root 6 is root 300, because 50 times 6 is 300. And then, are there any perfect square factors of 300? 100, yeah. So this becomes the square root of 100 times 3. And then what's the square root of 100? 10. So the answer is actually 10 root 3. So that's true. All right, I'm going to tell you this one's false. What's wrong with it? What's the mistake? Another really common mistake. Yeah, Jim?
They treated it as though subtracted regular 7 instead of negative 7.
Yeah, it's distributing the negative sign. Yep. So you did 3x minus 4x, right? So that gives you the negative x. And then you have to do the 5 minus negative 7, right? So it's minus a negative, so it ends up being plus, so that should be plus 12. So as it was written, it was false. How about number 10, true or false? True, yeah, we'll do the lobster claw or foil, whatever you call it. 8x squared minus 12x plus 2x minus 3, yeah, that's true. All right, now I got an equation to solve. What do you do when you have denominators in an equation? Like, I'd really just love for there to be no fractions. How do I make there to be no fractions? You cross multiply, you could multiply both sides by what? X. Yeah, if you multiply both sides by x, on the left, that makes the x's cancel, and you're just left with x squared plus 5x. And on the right, you distribute your x, and you get x cubed plus 5x. Okay, are those equal? Right. No. The only time those would be equal is when? It's equal in a couple of times. If x equals 1, yeah. When else? because whether you square 1 or cube 1, you still get 1 either way. So 1 will work. What other number will work? 0, yeah. Right. Only true when x equals 0 and when x equals 1. But in general, if I say, is this equation true? If it's not always true, you write false. Yeah. Something has to be always true to say true. All right. So that was really fast, I know, but we've got some more to do. I'm going to go through a few more with the exponent rules that we've been reviewing. And then I'm going to give you some more to try. Hopefully it's starting to come back to you a little bit. Okay, 64 times x to the 300 times y to the 600, all raised to the 1/3 power. All right, so when you raise, because these are all multiplication, there's times, and times, right? That's multiplication in there. Because it's all multiplication, I can raise each factor in the parentheses to that exponent, right? So this is actually equal to 64 to the 1/3 times x to the 300 to the 1/3 times y to the 600 to the 1/3. Raising something to the 1/3 power, right? Remember when you have a fractional exponent, the top is your power and the bottom is your root. So this is actually 64 to the 1st, which is 64, cube rooted. Anybody know the cube root of 64? 8 is the square root of 64. The cube root is 4. Yeah, because 4 times 4 is 16. 16 times 4 is 64. So this is 4, right? And then when you raise a power to a power, right? When you're raising a power to a power, what do you do to those powers? What's the rule? You multiply them. Good. Yeah. So there's two different exponent rules. When you're multiplying like exponents, you add them. When you're raising a power to a power, you multiply. So 300 times 1/3 is 100. And then 600 times 1/3 is 200. Yep. Okay, so 64 to the 1/3 is 64 to the 1st cube rooted, right? So whenever you have a fractional exponent, the top part of the fraction is the exponent on the number, and the bottom part of the fraction is actually a root that you're taking. So we're taking the cube root of 64, right? Because 64 to the 1st is 64. So then I just thought in my head, tried to come up with a number that when you multiply times itself 3 times, you get 64. Probably by the end of the semester, you'll be able to come up with it like that because we've seen it a bunch of times. You could also type in cube root of 64 in your calculator. It will give it to you. And it turns out it's 4 because 4 times 4 times 4 is 64. All right, let's look at 8 to the negative 2/3. First thing we got to deal with is the crying baby, right? You can't do anything if the baby's crying. So put this over 1, right? I've got this whole negative 2/3. That's my exponent. I gotta put it down, right? So the whole baby is gonna get moved down, and it's gonna be happy now. You put it down for a nap, not crying anymore. So what's left in the numerator when I moved the baby down? A 1. Good. So this is 1 over 8 to the positive 2/3. So this is 1 over, and let's translate this. The 2 is actually an exponent and the 3 is a root. So this is 8 squared cube rooted. And 8 squared is 64. And then what's the cube root of 64? 4. So this is 1/4. All right, radicals. I can't add and subtract radicals unless they're the same, right? They've got to be like terms to add and subtract them. So the root 12, let's simplify both of the radicals and we'll just like cross our fingers and hope that they come out as like terms. Okay, so root 12. Does 12 have any perfect square numbers that go into it? 4. So I'll rewrite 12 as 4 times 3. And then 27, does it have any perfect square factors? 9. Rewrite 27 as 9 times 3. Okay. And then the square root of 4, that's a square root I can actually take, right? What is the square root of 4? 2. So I copied that 3 down. And then instead of the square root of 4, I'm going to write a 2. And then I still have a square root 3. And then the square root of 9, I can take that square root, that is 3. And I still have a 3 under the square root. So this is 6 root 3 minus 3 root 3. Now those are like terms. 6 root 3 minus 3 root 3 is 3 root 3. It's the same as if it was like 6x minus 3x. Right? All right, factoring. Another big skill that is a prerequisite for this class, but you may have just learned it last semester, depending on what class you took before this. So factoring. In this case, I just want to pull out the GCF, right? So what's the biggest number that goes into both 5 and 45? 5. So I'm going to definitely pull out a 5. And what's the biggest number that goes into both x cubed and x? X. So I'm going to pull out a 5x. So this is like reverse distributing, right? So if I was going to distribute this 5x to something, what has to be the first term? 5x times what would give you 5x cubed? X squared, right? And 5x times what would give you negative 45x? Negative 9. But then what's really special about x squared minus 9? It can be factored more because 9 is a perfect square and x squared is a perfect square. So you have the difference of 2 squares, right? So I'm just going to copy the 5x. And then when you have the difference of 2 squares, it's going to factor to x plus 3, x minus 3. The square root of the x squared is the x. The square root of 9 is 3. So it's always going to be x plus 3, x minus 3. X plus the square root, x minus the square root. Familiar? Okay, good. All right, now I've got a fraction to reduce to lowest terms, which means I have to factor everything I can, and then hope some stuff cancels, right? So x squared plus 3x plus 10, can anybody factor that? Oh, so yeah, so there's actually, when you have a fraction bar, there's a sort of an I guess it is spoken. There's an assumption that you have parentheses around the entire numerator and the entire denominator. So this is an order of operations issue where you can't cancel anything that's separated by addition and subtraction, because the order of operations says you'd have to do all this addition before you can do the division. So you can't cancel unless things are separated by multiplication. So x squared plus 3x plus 10, what does that factor to? X plus 5 times x minus 2. Let's just double check with a quick FOIL. X squared minus 2x plus 5x, that does give me plus 3x minus 10. Good. And then my denominator, what does that factor to? X plus 4 times x minus 2. FOIL it out, you get x squared minus 2x plus 4x combines to 2x minus 8. Good. Are there any identical factors in the top and bottom of that fraction? X minus 2, so we can cancel those. And then my final result, when I reduce this, is x plus 5 over x plus 4. Liana, let me do something with numbers as opposed to x's to try to make it clear why you can't do that canceling thing that you suggested. You remembered? Okay, all right, good. I just felt like I didn't explain it very well. You know, I think it'd be good for everybody. Like, what if I had 6 plus 5 over 6 plus 4? If I do the order of operations, I'm supposed to add everything before I can divide. So this would be 11 over 10 or 1.1, right? But for some people, it would be tempting to cancel the 6's, right? And you'd be left with 5 over 4, which is 1.25, right? Which is not the actual answer, right? It's 1.1. So canceling when your numbers are separated by addition doesn't work, right? So this is actually not true, that second one. You got to do the addition and subtraction before you can cancel. Or factor things so that they're only separated by multiplication, right? Like here, what allowed us to cancel is that these are times right there. Okay, last example, and then I'm going to put you back to work for the last 10 minutes. I'm going to add these two fractions. What do you need to be able to add two fractions together? A common denominator. What's the common denominator going to be? Yeah, x squared minus 4, which is x plus 2 times x minus 2, right? So 3x over x plus 2. Yeah, actually extend that, plus x over x minus 2. So I need them to have the same denominator, and you can always, to get the same denominator, you multiply the top and bottom of a fraction by something, right? So this first fraction needs an x minus 2. So I put an x minus 2 in the denominator, and then you also have to multiply the numerator by the same thing, right? Because multiplying by x minus 2 over x minus 2 is just multiplying by 1, and you're not changing anything. And then on the right, my denominator needs an x plus 2. So I multiply by x plus 2 on the bottom and the top. Okay. Then I'm just going to do my distributing on the numerator. So I get 3x squared minus 6x over x plus 2, x minus 2, plus x squared plus 2x, just distribute that x, over x plus 2, x minus 2. And then I can combine like terms in the numerators. 3x squared plus x squared is 4x squared. Negative 6x plus 2x is negative 4. Over x plus 2, x minus 2. If you notice that your numerator can factor, you should probably factor it to see if anything cancels. So I can pull out, I'm doing this really fast because we've already gone over that kind of factoring. Do I have any factors that are exactly the same on the top and the bottom? No. So that's just my answer. Nothing cancels. That would be fine. This would be fine. So would that. Any of those answers would be completely acceptable. All right, so most days I'm not going to go over the whole preview exercises, and they won't be as long as today's either. I was just trying to squeeze in a lot of review. So we've got only 5 minutes left, which is not as much as I had hoped, but I would like you to start the class activities. And then right after that, just want to point out that the last page has the answers to all the class activities, so you can check them as you go. And if you don't get a chance ever in general to finish them in class, you should do them on your own. And then after that, the homework is all listed, right? Homework, learning objectives, things you should know how to do, and then preparation for the next class. All right, so go ahead and start those activities. We can work for 5 minutes, and after that, I'll just see you Friday.